What if I told you we're about to break every limit of human imagination? Tonight, we're going to travel from Earth to the absolute edge of existence at light speed. You've heard the universe is big. You've seen Earth as a tiny dot in space comparisons. But here's what most people don't realize. The universe's true scale doesn't just challenge comprehension. It obliterates every category of thought we possess. By the end of this journey, you'll understand why astronomers stare into telescopes with wonder and existential terror. You'll see reality itself in a completely different way. Before we dive in, if you enjoy these explorations, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a real difference for me. Settle in. We're about to shatter everything. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Lift off. We're traveling at the speed of light instantly, 186,000 miles per second, slicing through the vacuum of space. You might think you understand what this means, but let me put this in perspective for you. Every second that passes, we're covering a distance that would take you 5.5 hours to drive on the highway. Every single second. Through the window, we watch the International Space Station flash by like a silver streak at 250 miles above Earth. Astronauts floating inside, completely unaware of our passage, going about their daily routines in that tiny outpost of humanity suspended in the void. Think about that for a moment. Those astronauts represent the farthest that most humans have ever traveled from home, and to us, they're already a memory disappearing behind us. And look, our first stop is already approaching. The moon awaits us at just 1.28 seconds of travel. Stop 1, the moon. 1.28 seconds, 238,900 miles from Earth. The lunar surface stretches before us, grey and cratered. A landscape that has remained essentially unchanged for 4 billion years. These craters are witnesses to the cataclysmic bombardment of the young solar system, when massive rocks hurled through space at unimaginable speeds, carving permanent scars into worlds that had no atmosphere to protect them. You've probably seen the moon thousands of times from Earth, but being here, the silence is absolute. There's no wind, no weather, no erosion of any kind. The footprints that Neil Armstrong left in 1969 will remain intact for millions of years. Think about that. Millions of years from now, when civilizations we can't even imagine look back at this moment in history, those footprints will still be here, perfectly preserved. The lunar seas you see spread across the surface, the Maria, as astronomers call them, aren't seas at all. They're vast plains of solidified lava from when the moon was still geologically alive, still hot enough for molten rock to flow across its surface like slow grey rivers. That was 3.5 billion years ago, when Earth itself was still a violent, barely recognizable world. Here's something that might help you grasp the scale we're dealing with. If Earth were a basketball, the moon would be a tennis ball orbiting at 23 feet away. Most people imagine the moon much closer than it actually is. In reality, you could fit every planet in our solar system in the space between Earth and moon, with room to spare. The temperatures here swing violently without an atmosphere to moderate them. In direct sunlight, the surface reaches 260 degrees Fahrenheit. Hot enough to boil water instantly. In the perpetual darkness of lunar night, temperatures plunge to minus 273 degrees. That's colder than anywhere on Earth, colder than the deepest space missions have ever recorded. But here's something extraordinary about our moon. It's slowly moving away from us. Each year, the moon drifts 1.5 inches farther from Earth. 3.2 billion years ago, it orbited at only 168,000 miles away. Back then, if you could have stood on the ancient Earth and looked up, the moon would have appeared 3 times larger in the sky. Tides would have been catastrophic. Days would have lasted only 5 hours, and the night sky would have been dominated by this enormous grey sphere. A complete lunar day lasts 29.5 Earth days. This is why we always see the same face of the moon from Earth. It's tidally locked, rotating once for every orbit. But here's what's fascinating. The far side of the moon, the side we never see from Earth, has a crust that's 31 miles thicker than the near side. Scientists think this happened because of asymmetric impacts during the moon's violent formation. Standing here on the lunar surface and looking back at Earth, our home planet appears 4 times larger than the moon appears from Earth. It hangs there as a blue and white marble against the absolute black of space, the only color in an otherwise gray and black universe visible from here. No matter where you are on the moon, Earth never moves in the sky. It just hangs there, always in the same position, slowly rotating to show you different continents. The silence here is unlike anything you've ever experienced. It's not just quiet, it's the complete absence of sound. No air means no medium for sound waves to travel. You could stand next to a massive boulder rolling down a crater wall, and you'd hear absolutely nothing. The only sounds would be the ones conducted through your body or your equipment. During the Apollo missions, astronauts reported that the moon has a smell. When they brought lunar dust into their spacecraft, it smelled like gunpowder or spent fireworks. This dust, called regolith, is incredibly fine, created by 4 billion years of meteorite impacts, grinding rock into a powder so fine it sticks to everything and is nearly impossible to clean off. Time to catch our flight again. We're lifting off toward the sun, which awaits us 8 minutes and 20 seconds ahead in our journey. As we leave the moon behind, it shrinks back to a grey disk, then to a point of light, and finally becomes just another star in the vast darkness we're traveling through. Stop 2. The Sun. 8 minutes 20 seconds from the Moon, 93 million miles from Earth. We navigate through the interplanetary void, where density drops to fewer than 5 atoms per cubic centimeter. This is emptiness on a scale that's hard to comprehend. The space between planets isn't just mostly empty. It's more empty than any vacuum we can create on Earth. Yet somehow, this void carries the solar wind, carries magnetic fields, carries the influence of our sun across billions of miles. At 3 minutes into our journey, Mercury flashes past our window, an infernal world where daytime temperatures reach 806 degrees Fahrenheit, while nighttime plunges to minus 292 degrees. Mercury's iron core occupies 85% of the planet's radius, making it the second densest planet in our solar system. If you could somehow stand on Mercury's surface during its day, the Sun would appear 2.5 times larger than it does from Earth. At 5 minutes, Venus appears to our right, a world wrapped in crushing atmosphere 92 times thicker than Earth's. The pressure there would be like being half a mile underwater in Earth's oceans. And it rains sulfuric acid, though that acid never reaches the surface. It evaporates in the 867-degree heat, long before it could touch the ground. And now, here we are at our Sun. The Sun dominates everything as a sphere of plasma, 864,000 miles in diameter. If the Sun were a basketball, Earth would be a peppercorn orbiting at 82 feet away. This distance we've just traveled, 93 million miles, defines what astronomers call the astronomical unit, or AU, the fundamental measuring stick for distances within our solar system. But what exactly are we looking at here? The Sun's surface reaches 9,940 degrees Fahrenheit, yet that's nothing compared to its core, which maintains an incomprehensible 27 million degrees. At these temperatures, matter behaves in ways that would seem like magic to us. Electrons are stripped from atoms, creating a soup of charged particles called plasma. Every second, 660 million tons of hydrogen transmute into helium through nuclear fusion. This might sound abstract, but let me put it in perspective. The fusion happening in the sun's core every single second releases energy equivalent to 1 million hydrogen bombs, each with the power of 100 megatons, all detonating simultaneously. Every second. For 4.6 billion years, the light that's hitting us right now began its journey in the sun's core somewhere between 100,000 and 1 million years ago. Those photons have been bouncing around inside the sun all this time, ricocheting trillions upon trillions of times as they slowly worked their way from the core to the surface. Once they finally broke free from the sun's surface, they raced to us in just 8 minutes and 20 seconds. Look at those dark patches on the sun's surface, sunspots. They appear dark, but they're still 6,800 degrees Fahrenheit, hot enough to vaporize any metal instantly. These are regions where the sun's magnetic field is so intense it actually suppresses convection, making these areas slightly cooler than the surrounding surface. Slightly cooler, but still hot enough to melt tungsten. Those magnificent arcing structures rising above the sun's surface are called prominences. They tower 62,000 miles above the surface. That's equivalent to nearly 8 Earths stacked on top of each other. These are loops of plasma following magnetic field lines, held aloft by magnetic forces so powerful they can suspend material thousands of times denser than our atmosphere. The sun's magnetic field completely flips its polarity approximately every 11 years. During these solar cycles, the sun's activity waxes and wanes. During solar maximum, the sun becomes violent and active, hurling massive ejections of plasma into space. During solar minimum, it becomes relatively calm. We're watching a star that breathes, that pulses, that has moods and cycles. Here's something that might humble you. In 5 billion years, when the sun begins to run out of hydrogen fuel in its core, it will expand into a red giant star. It will grow so large that its surface will extend beyond the orbit of Mars. Mercury will be vaporized, Venus will be vaporized, and Earth. Earth might survive as a charred cinder, or it might be engulfed entirely. The sun that gives us life, that makes everything possible, will eventually consume the very world it nurtured. But that's 5 billion years in the future. For perspective, 5 billion years ago, Earth itself was still forming. Life was just beginning to emerge. The entire history of complex life on Earth, from the first fish to dinosaurs to humans, could happen twice over before the sun begins its final transformation. Time to catch our flight again, lifting off toward Mars, which awaits us 12.5 additional minutes ahead in our cosmic journey. We quickly cross Earth's orbital path, leaving behind the familiar territory of our home planet's neighborhood. As we travel deeper into the solar system, fragments from the asteroid belt begin to dot the darkness to our right. These are the leftover building blocks of planets that never formed, rocky remnants from the violent birth of our solar system 4.6 billion years ago. At 3 minutes into our journey toward Mars, we catch sight of something fascinating. Phobos, racing around Mars in its swift orbit. This tiny moon rises in the west and sets in the east. The opposite of what we're used to on Earth. And here's something both remarkable and tragic about Phobos. It's slowly falling toward Mars, sinking about 6 feet every century. In 50 million years, this small moon will be torn apart by Mars' gravity and scattered into a ring system around the red planet. Stop 3. Mars. 12.5 additional minutes. 142 million miles from the sun. Mars presents itself to us in rusty red glory, 4,212 miles in diameter, roughly half the size of Earth. That distinctive reddish coloration that makes Mars visible to the naked eye from Earth comes from iron oxide on its surface. Essentially, Mars is red because it's rusty. The entire planet is covered in a fine layer of oxidized iron dust, like a world-sized desert of rust particles. Look at that massive mountain rising from the Martian surface. Olympus Mons towers 13 miles above the surrounding plains. To put that in perspective, that's like stacking 3 Mount Everests on top of each other. The base of this extinct volcano spans an area roughly the size of the state of Arizona. If you stood at the base of Olympus Mons and looked up, the summit would be beyond the horizon. You literally couldn't see the top because of the planet's curvature, and that enormous gash cutting across Mars like a massive scar. That's Valles Marineris, stretching 2,500 miles across the planet and reaching depths of 4 miles. This canyon system is so vast that the entire continental United States could fit inside it. It's not just one canyon, but a complex system of interconnected valleys that formed over billions of years through a combination of geological processes we're still trying to understand. The atmosphere here is incredibly thin, containing only 1% of Earth's atmospheric density. Temperatures vary wildly from 68 degrees Fahrenheit at the equator during summer to minus 195 degrees at the poles. Without a thick atmosphere to moderate temperature swings, Mars experiences some of the most extreme daily temperature variations in the solar system. Occasionally, Mars experiences global dust storms that can envelop the entire planet for months at a time. These storms transform the normally pinkish Martian sky into an opaque orange haze, blocking out the sun and creating an otherworldly twilight that can last for weeks. During these storms, the temperature differences between day and night become even more extreme as sunlight struggles to penetrate the dust-filled atmosphere. But here's what makes Mars truly fascinating. There's overwhelming geological evidence that this planet once had liquid water oceans 3.8 billion years ago. Back then, Mars was warm and wet, with a much thicker atmosphere that could support liquid water on its surface. Scientists have found unmistakable evidence of ancient shorelines, river deltas, and mineral formations that could only have formed in the presence of abundant liquid water. Those dry valleys and fossilized river deltas preserve the record of flowing rivers that once carried enormous volumes of water across the Martian surface. You can see the braided patterns where multiple river channels once meandered across plains that are now bone-dry and frozen. These aren't just small streams. Some of these ancient rivers were massive, carrying more water than the Amazon River does today. The polar ice caps contain frozen water mixed with dry ice. Frozen carbon dioxide. During the Martian winter, temperatures become so cold that 30% of the planet's atmosphere actually freezes and deposits at the poles. As spring returns to each hemisphere, this frozen atmosphere sublimates back into gas, creating seasonal atmospheric pressure changes across the entire planet. Right now, as we speak, there are rovers exploring Mars. Curiosity and Perseverance are trundling across the Martian surface, searching for evidence of past or present microbial life. These robotic explorers are drilling into rocks, analyzing soil samples, and slowly building our understanding of whether Mars ever harbored life. Every day they operate represents another chapter in humanity's quest to answer one of the most profound questions we can ask: are we alone? Mars has a second moon, Deimos, orbiting much farther out with a diameter of only 9 miles. Its irregular shape suggests it's probably a captured asteroid, a piece of space rock that wandered too close to Mars and was gravitationally snared into orbit. Unlike Phobos, which races around Mars in less than 8 hours, Deimos takes 30 hours to complete one orbit, longer than a Martian day. As we begin this longer journey into the outer solar system, we can already see Saturn in the distance, a golden disk with thin, bright rings, a cosmic jewel awaiting us further ahead in our voyage. Stop. 4. Jupiter. 43 additional minutes. 484 million miles from the Sun, 5.2 AU. We pass through the asteroid belt during our journey. At 28 minutes, Ceres appears with its 584-mile diameter and bright white spots of crystallized salt gleaming on its surface. The asteroid belt contains millions of rocky fragments, but here's something that might surprise you. The total mass of all these asteroids combined equals only 4% of our moon's mass. Despite what science fiction movies might suggest, these asteroids are separated by millions of miles of empty space. And now, Jupiter dominates our view like nothing we've encountered so far. Jupiter commands the space around it with a mass 318 times greater than Earth. This single planet outweighs all the other planets in our solar system combined. To put Jupiter's immense size in perspective, you could fit 1,300 Earths inside its volume. If Earth were a marble, Jupiter would be a basketball sitting next to it. That enormous oval feature you see is the Great Red Spot, appearing like a gigantic eye staring back at us. This is a storm that has been raging continuously for at least 350 years, longer than the United States has existed as a nation. Currently, it spans about 10,000 miles in diameter, which means you could drop Earth into this storm and it would rattle around like a marble in a fishbowl. Mysteriously, the Great Red Spot is shrinking. When astronomers first began keeping detailed records in 1800, it measured 25,000 miles across. For unknown reasons, this ancient storm is slowly contracting, though the winds at its edges still rage at 400 miles per hour, perpetually furious winds that make Earth's most powerful hurricanes look like gentle breezes. Jupiter possesses a magnetic field 20,000 times more intense than Earth's. This magnetosphere extends 4.3 million miles into space, creating a bubble of magnetic influence that's larger than the Sun itself. If you could see Jupiter's magnetosphere with your naked eyes, it would appear larger than the full moon in Earth's sky. Despite Jupiter's colossal size, a Jupiterian day lasts only 9.9 hours. This gas giant spins faster than any other planet in our solar system. The rapid rotation creates the distinctive bands and swirls you can see in Jupiter's atmosphere. These are jet streams of ammonia and methane racing around the planet at hundreds of miles per hour. Look at those 4 bright dots orbiting Jupiter. Those are the Galilean moons discovered by Galileo 400 years ago. Europa, one of these moons, hides a global ocean 62 miles deep beneath its icy crust. This subsurface ocean contains more water than all of Earth's oceans combined. The reddish cracks you can see streaking across Europa's surface suggest recent geological activity where salty water has seeped up through the ice, making Europa one of the most promising places to search for alien life in our solar system. Io, the innermost Galilean moon, suffers gravitational distortions so intense that its crust rises and falls 330 feet with each orbit. This constant flexing keeps Io's interior molten, maintaining 400 active volcanoes simultaneously. Yellow sulfur lava shoots 186 miles above Io's surface, making it the most volcanically active body in the entire solar system. Ganymede exceeds Mercury in size, with a diameter of 3,273 miles, and it possesses its own magnetic field. This makes Ganymede the only moon in our solar system with a detectable magnetosphere. It's larger than the planet Mercury, yet it orbits another planet rather than the Sun directly. Jupiter currently has 95 confirmed moons, making it the most populous lunar system known in our solar system. These range from massive worlds like Ganymede down to tiny captured asteroids only a few miles across. Jupiter is essentially a miniature solar system unto itself, with its own family of worlds held in gravitational embrace. During our journey into the outer reaches of our solar system, we pass some of the most magnificent sights in our cosmic neighborhood. At 49 minutes into our flight, Saturn glides past to our left, that golden jewel with its impossible rings stretching 174,000 miles across, but only 33 feet thick. Imagine a DVD disc scaled up to the size of a football field. That's how impossibly thin Saturn's rings are relative to their width. And there's something peculiar at Saturn's North Pole. A perfect hexagon 30,000 miles across. This geometric shape has been spinning at Saturn's pole for decades, a six-sided storm larger than Earth itself. Scientists still don't fully understand how nature creates such precise geometry on such a massive scale. Titan, Saturn's largest moon, orbits with liquid methane lakes gleaming on its surface. This is the only moon in our solar system with a dense atmosphere, thicker than Earth's own. On Titan, it rains liquid methane, and rivers of hydrocarbons flow into seas of liquid natural gas. It's like an alien version of Earth's water cycle, but running on chemistry that would be explosive in our oxygen-rich atmosphere. At 1 hour and 15 minutes, Uranus appears to our right, and something's clearly wrong with this planet. It's lying on its side. Uranus has an axial tilt of 98 degrees, which means it essentially rolls along its orbital path, rather than spinning upright like other planets. Each pole faces the Sun for 42 years of continuous daylight, followed by 42 years of complete darkness. Imagine seasons that last longer than a human lifetime. At 2 hours and 20 minutes, distant Pluto appears as a reddish speck. That bright heart-shaped feature on its surface is frozen nitrogen, and Pluto's moon Charon is so large relative to Pluto that both objects actually orbit around a point in space between them. They're essentially a double-planet system, locked in an eternal dance at the edge of our solar system. Stop 5. Neptune. 2.5 additional hours, 2.8 billion miles from the Sun, 30 AU. Neptune presents itself in intense blue glory, its color created by methane in its atmosphere absorbing red light. But what makes Neptune truly remarkable isn't just its stunning appearance. It's the violence of its weather. This distant world experiences the most ferocious winds in our entire solar system, reaching speeds of 1,240 miles per hour. To put that in perspective, those are winds 3 times faster than the strongest hurricanes ever recorded on Earth. That dark oval you might glimpse is Neptune's great dark spot, or rather, it was. When Voyager 2 observed Neptune in 1989, it saw a massive storm system the size of Earth. But when the Hubble Space Telescope looked at Neptune in 1994, that great dark spot had mysteriously vanished, replaced by a new dark spot in a completely different location. Neptune's atmosphere is so dynamic that storm systems the size of Earth can simply disappear within a few years. Here's something that puzzles scientists. Neptune radiates 2.6 times more energy than it receives from the Sun. At this distance, sunlight is 1,000 times weaker than it is on Earth, yet Neptune somehow generates internal heat from an unknown source. This internal energy drives those incredible winds and powers, the dynamic weather systems that constantly reshape the planet's appearance. A Neptunian day lasts 16 hours, while a Neptunian year stretches across 165 Earth years. Since Neptune's discovery in 1846, it has completed only one full orbit around the Sun. The Neptune that we're looking at now has returned to roughly the same position in space that it occupied when our great-great-great-grandparents were alive. Triton, Neptune's largest moon, orbits in the opposite direction from all other major moons in the solar system. This retrograde motion tells us that Triton wasn't born here. It was captured from the Kuiper Belt by Neptune's powerful gravity. Triton's surface reaches -391 degrees Fahrenheit, making it one of the coldest places in our solar system. Yet even at these frigid temperatures, Triton is geologically active. Geysers of liquid nitrogen explode 5 miles above its frozen surface. These nitrogen geysers create dark streaks across Triton's ice as the erupted material falls back down and is blown by thin winds in the tenuous atmosphere. Neptune holds a special place in the history of astronomy. It was the first planet discovered through mathematical prediction rather than direct observation. In 1846, astronomers noticed that Uranus wasn't following its predicted orbital path. They calculated that another massive planet must be pulling on Uranus gravitationally, and when they pointed their telescopes to the predicted location, there was Neptune, exactly where the mathematics said it should be. Only one spacecraft has ever visited Neptune. Voyager 2 flew past in 1989, and it remains the only probe to examine this distant world up close. Everything we know about Neptune in detail comes from that single encounter over 35 years ago. Unlike Mars, which hosts multiple rovers, or Jupiter, which has been visited by several spacecraft, Neptune remains largely mysterious, accessible only to our most powerful telescopes. Time to catch our flight again, lifting off toward the heliopause, the magnetic boundary of our solar system, which awaits us 5 additional hours ahead. As we begin this longest journey yet, objects from the Kuiper Belt start to appear like floating icebergs in space. There's Makemake and Haumea spinning in the shape of a rugby ball, remnants from the early formation of our solar system. Stop 6. The heliopause. 5 additional hours, 11.2 billion miles, 120 AU from the Sun. During our 5-hour journey, dozens of trans-Neptunian objects pass by our windows, frozen relics from the formation of our solar system. These are the leftover building blocks that never quite made it into planets, preserved in the deep freeze of the outer solar system for 4.6 billion years. They're time capsules, containing the original materials from which our solar system formed. Eris appears in the distance with a mass 27% greater than Pluto. It was the discovery of Eris in 2005 that forced astronomers to reclassify Pluto as a dwarf planet. If Pluto deserved to be called a planet, then so did Eris. Rather than add dozens of new planets to our solar system, astronomers chose to create a new category, dwarf planets, and moved Pluto into it. At 4 hours and 47 minutes into our journey, something epic happens. Voyager 1 appears in our window, a small golden flash with its dish antenna slowly rotating. This tiny spacecraft, launched in 1977, has been traveling at 38,000 miles per hour for 47 years to reach this point. We've covered the same distance in just 5 hours at the speed of light. Voyager 1 carries the golden record, a collection of sounds and images from Earth intended for any alien civilization that might find it. This small spacecraft carries the sounds of wind, rain, surf, birds, whales, and human music. It contains greetings in 59 languages and photographs showing the diversity of life on Earth. Right now, as we pass it, Voyager 1 is carrying Earth's message to the stars. The heliopause marks the boundary where the solar wind collides with the interstellar medium, creating an invisible but measurable shock wave. This isn't a physical barrier you could touch. It's the place where the stream of charged particles flowing out from our sun meets the thin gas that fills the space between stars. Voyager 1 crossed the heliopause in 2012, becoming the first human-made object to enter genuine interstellar space. Voyager 2 followed in 2018. These twin spacecraft are now humanity's first ambassadors to the galaxy, carrying our message beyond the realm of our sun's influence. Beyond this point, the density of galactic cosmic rays increases 9 times. The Sun's magnetic field, which has protected our entire solar system from much of the galaxy's radiation, no longer dominates here. Interstellar radiation penetrates freely, no longer deflected by our Sun's magnetic embrace. The temperature of space plasma drops dramatically as we cross this magnetic frontier, from millions of degrees to tens of thousands. Voyager's instruments detected this change as a distinct shift in the sound of space. The spacecraft recorded a different hum from the interstellar plasma, with a frequency distinct from the solar environment. The shape of the heliopause is asymmetric because our entire solar system is moving through interstellar space. Our Sun races through the galaxy at 58,000 miles per hour toward the constellation Hercules, pushing against the interstellar medium like a boat creating a bow wave. On the front side, where our solar system plows ahead, the heliopause lies at about 120 AU. On the trailing side, it stretches out to 300 AU, forming a comet-like tail behind us. But this isn't yet the gravitational boundary of our solar system. This is merely the magnetic frontier where our Sun's dominion ends. The Sun's gravity still holds sway much farther out, keeping vast numbers of comets in distant orbits that we're about to discover. As we accelerate away from the heliopause, our Sun begins to shrink rapidly, transforming from the brilliant disk that has dominated our journey into just another star among thousands of points of light scattered across the cosmic darkness. During the first 3 months of continuous travel, trillions of frozen cometary nuclei begin to dot the space around us. These are the sleeping giants of our solar system, ancient remnants that have been waiting in the cold darkness for billions of years. Each one is a time capsule, preserving materials from the very formation of our solar system, untouched by the heat and radiation that has transformed the inner planets. By 6 months into our journey, every 621,000 miles, we pass another dormant comet. Dirty snowballs the size of mountains drifting in lazy orbits. These aren't the spectacular comets with glowing tails that occasionally grace our skies. Those are what happen when one of these frozen chunks gets knocked toward the inner solar system and begins to sublime in the Sun's heat. Out here, they're just dark, silent ice mountains floating in the eternal night. At 10 months into our year-long journey, something remarkable begins to happen. Distant stellar objects start to appear as close as our Sun once seemed. Proxima Centauri glows red ahead of us at 3.2 light-years away. From this distance, the nearest stars to our solar system no longer seem impossibly distant. They're becoming our new neighbors. Alpha Centauri A and B form a bright yellow double point. This binary star system awaits us further ahead in our progressive journey through space. These two stars are locked in an eternal gravitational dance, orbiting around each other in a cosmic waltz that takes 80 years to complete. Stop 7, the Oort cloud. 1 complete year of travel, 5.9 trillion miles, 1 light-year from the Sun. The Oort cloud marks the true gravitational boundary of our solar system. Beyond here, our Sun's gravity finally loses its dominion over objects in space. This isn't a sharp boundary like a wall. It's more like the edge of a sphere of influence that gradually fades away into the gravitational pull of other stars. This spherical cloud extends outward to 100,000 AU, or 1.5 light-years, almost 1/3 of the way to Proxima Centauri. To help you understand this scale, imagine our entire journey so far. From Earth to Neptune, past the heliopause and out to where we are now. That's still only a tiny fraction of the Oort cloud's full extent. The Oort cloud contains an estimated 2 trillion comets in orbits that take millions of years to complete 1 revolution around the distant Sun. These aren't the quick 90-day orbits we're familiar with in the inner solar system. Out here, orbital periods are measured in geological timescales. A single orbit for one of these distant comets might span the entire rise and fall of civilizations on Earth. When nearby stars pass close to our solar system, they gravitationally disturb these distant orbits, sending comets tumbling toward the inner solar system. This is where visible comets come from. They're visitors from this distant realm, falling sunward after spending millions of years in the outer darkness. Every spectacular comet that has ever graced Earth's skies began its journey here, in this vast repository of frozen relics. The Oort cloud formed from planetesimals ejected by Jupiter and Neptune during the violent formation of our solar system 4.6 billion years ago. When our solar system was young and chaotic, these massive planets acted like gravitational slingshots, hurling countless chunks of rock and ice into the outer darkness. What should have become part of the planets instead became this vast spherical shell of debris. The total mass of the Oort cloud may equal several times Earth's mass, but it's spread across a volume so colossal and empty that the average distance between objects is measured in billions of miles. If you were somehow transported to a random location in the Oort cloud, the nearest comet would likely be farther away than Pluto is from our Sun. Its emptiness on a scale that challenges comprehension. Voyager 1 will take more than 300 years to reach this region and approximately 30,000 years to travel completely through it. Think about that for a moment. This little spacecraft that we passed just hours ago in our light-speed journey will spend longer crossing the Oort cloud than humans have existed as a species. When Voyager 1 finally emerges from the far side of the Oort cloud, Earth will be inhabited by beings we can't even imagine. Here ends our natal neighborhood. Everything beyond belongs to the domain of stars and deep interstellar space. We've reached the edge of home, the place where our solar system finally gives way to the galaxy at large. Time to catch our flight again, departing for our first true interstellar journey. Proxima Centauri awaits us 3.2 additional years of travel ahead. Our Sun transforms from the center of everything into just another star among thousands. No longer the commanding presence that has dominated our journey, but merely a bright yellow point of light in the distance. Stop 8, Proxima Centauri. 3.2 additional years, 25 trillion miles, 4.2 light-years from Earth. During our first additional year of travel, Alpha Centauri A and B grow larger to our left, this binary star system where two stars orbit each other every 80 years. These stellar companions dance separated by 23 times the Earth-Sun distance, performing a perpetual gravitational waltz through interstellar space. From our perspective, we can watch this cosmic choreography unfold, two suns locked in an ancient embrace. At 2.5 years of travel, Barnard's star passes to our right at 5.9 light-years distance, a red dwarf racing through space at 88,000 miles per hour. This shy star possesses at least one planet in its habitable zone, a potentially rocky world orbiting this swift and timid stellar wanderer. Barnard's star is one of our Sun's closest neighbors, yet it's so faint that it remains invisible to the naked eye despite its proximity. Proxima Centauri is a red dwarf with only 12% of our Sun's mass. If our Sun were a basketball, Proxima would be a tennis ball sitting beside it. This tiny star is so faint that despite being the closest star to our solar system, it's completely invisible to the naked eye from Earth. Its apparent magnitude is only +11, requiring a telescope to see it at all. This diminutive star hosts a rocky planet called Proxima b in its habitable zone, orbiting every 11 days. Here's a potential home for alien life just 4.2 light-years from our own world. Proxima b receives roughly the same amount of stellar energy that Earth gets from our Sun. But because its star is so much cooler and dimmer, the planet must orbit much closer. so close that it's probably tidally locked, with one side permanently facing the star and the other locked in eternal night. Proxima is what astronomers call a flare star. It suffers sudden eruptions that can increase its brightness by 68% within minutes. These stellar tantrums flood the surrounding space with radiation, periodically bombarding any planets in the system. If life exists on Proxima b, it would need to be incredibly hardy to survive these periodic radiation baths. This little star will live for 4 trillion years, nearly 1,000 times longer than our Sun will shine. Due to its slow fusion rate and extreme economy with its hydrogen fuel, Proxima Centauri will still be glowing red when our Sun has long since exhausted its nuclear fuel and faded to a cold white dwarf. In the far future, when our solar system is dark and frozen, Proxima will still be warming its little family of worlds. Interestingly, this star is slowly approaching us. At 50,000 miles per hour, in 26,700 years it will reach its closest approach at just 3.11 light-years away. Even the stars themselves are in motion, slowly changing the shape of our cosmic neighborhood over tens of thousands of years. Proxima's surface temperature reaches only 5,500 degrees Fahrenheit. It glows in deep red, almost at the edge of invisible infrared. This is a star that burns so cool and dim that if it replaced our Sun, Earth would be a frozen wasteland. Yet in its own quiet way, Proxima represents hope. Hope that even the smallest, most modest stars can nurture worlds where life might take hold. Time to catch our flight again, lifting off towards Sirius, the brightest star in Earth's sky, which awaits us 4.4 additional years of travel. During our journey, dozens of nearby stellar systems dot the space around us. Wolf 359 lies at 7.8 light-years, with only 10% of our Sun's mass, and Lalande 21185 passes distantly at 8.3 light-years. An ancient red dwarf with 46% of our Sun's mass and its own planetary system in orbit. We're now truly in interstellar space, where distances are measured not in miles or even astronomical units, but in the time it takes light itself to cross the emptiness between suns. Each year of our journey at light speed represents 6 trillion miles of travel through a universe so vast that even light, the fastest thing in existence, takes years to bridge the gaps between stellar neighbors. At 2 additional years of travel, Ross 154 passes as a reddish point. A red dwarf so faint it would be invisible even at 32 light-years distance. This dim star represents the majority of stars in our galaxy. Small, cool, and incredibly long-lived, but so faint that they remain hidden from casual observation despite being our cosmic neighbors. Dark molecular clouds begin to block entire regions in the distance, stellar nurseries where new stars will be born in millions of years. These vast clouds of gas and dust appear as dark patches against the starfield, but they're actually some of the most important structures in the galaxy. Within these seemingly empty voids, gravity is slowly gathering material together, compressing it until nuclear fusion ignites and new suns are born. Stop 9. Sirius. 4.4 additional years, 50 trillion miles, 8.6 light-years from Earth. Sirius blazes before us as the brightest star in Earth's night sky, with an apparent magnitude of -1.46. This cosmic beacon has guided navigators and inspired cultures for thousands of years. When you look up at the winter sky from Earth and see that brilliant blue-white star outshining everything else, you're looking at the stellar lighthouse we now approach. But Sirius isn't just one star. It's a binary system where Sirius A, a blue-white star twice as massive as our Sun, orbits with its companion Sirius B every 50 years. These 2 stars are locked in an eternal gravitational dance, circling around their common center of mass in a cosmic waltz that takes half a century to complete. Sirius B represents one of the strangest objects in the universe, a white dwarf, which is essentially a stellar corpse the size of Earth, but containing the complete mass of our Sun. This means Sirius B has a density 1 million times greater than water. To help you comprehend this impossible density, a teaspoon of material from Sirius B would weigh 11,000 pounds, as much as a large truck compressed into something you could hold in your hand. This is matter compressed beyond normal comprehension. Degenerate matter squeezed by gravity until electrons and atomic nuclei exist in states that would be impossible under normal conditions. When Sirius B was a normal star millions of years ago, it exhausted its nuclear fuel and collapsed under its own gravity, crushing a star's worth of material into a sphere smaller than our planet. Sirius A burns with a surface temperature of 17,900 degrees Fahrenheit, nearly twice as hot as our Sun, which gives it that distinctive blue-white brilliance. This intense heat makes Sirius A incredibly luminous, outshining our Sun by 25 times, despite being only twice as massive. It's a star that burns bright and fast, consuming its nuclear fuel at a prodigious rate. Ancient Egyptians based their calendar on Sirius. When this bright star appeared just before dawn, they knew the Nile River would soon flood, bringing fertile silt to their agricultural lands. They called it Sopdet, and its heliacal rising marked the beginning of their year. For thousands of years, this distant star governed the rhythm of human civilization along the Nile. Sirius is slowly approaching us at 12,000 miles per hour. In 60,000 years, it will become the closest star to our solar system, temporarily replacing Proxima Centauri as our nearest stellar neighbor. The night sky that our distant descendants see will be subtly different from ours, as the slow dance of stars gradually reshapes the constellations over tens of thousands of years. Think about this for a moment. For every 10 human generations that have passed since our first stop at the moon, we are now encountering the great-great-grandchildren of our original crew members commanding this vessel. Time has taken on a different meaning at these scales. The humans who began this journey have become ancestors, whose stories are passed down through generations born among the stars. Time to catch our flight again, now departing for a gigantic leap of 541.4 years to Betelgeuse, the red supergiant awaiting us. During this century-spanning voyage, generations will succeed one another aboard our vessel, and the stories of Earth will transform from living memory into legends told by ancestors. During our journey across the centuries, stellar formations begin to reveal themselves in their full grandeur. At 50 years of travel, the Pleiades cluster appears to our right. 800 young blue stars born together 100 million years ago. These stellar siblings shine with the brilliant blue-white light of youth, hot, massive stars that will burn fast and die young, their lives measured in tens of millions rather than billions of years. At 200 years into our voyage, the Orion Nebula explodes in colors to our left, a stellar maternity ward where 700 stars are being born simultaneously. This is ionized gas made luminous by the intense radiation from newborn stars, a cosmic cathedral of creation where the raw materials of space are being forged into new suns. The nebula glows red from hydrogen, blue from oxygen, creating an artwork painted in the fundamental elements of the universe. Stop 10. Betelgeuse. 541.4 additional years, 3.2 quadrillion miles, 550 light-years from Earth. At 400 years of travel, the Helix Nebula appears distantly at 655 light-years, the Eye of God, where a dying star has ejected its outer layers. This is a planetary nebula, a ring of gas expanding at 25 miles per second. The future fate of our own sun in 5 billion years, when it exhausts its nuclear fuel and sheds its outer atmosphere into space. Betelgeuse dominates our view as a red supergiant with a diameter 1,400 times larger than our sun. If this massive star replaced our sun, it would engulf everything out to nearly Jupiter's orbit. The scale is so immense that our entire inner solar system would fit comfortably within this single star's atmosphere. This is a star with the mass of 16 to 19 suns, compressed into a pulsating giant that oscillates in diameter by 60% every 400 days. Betelgeuse breathes like a cosmic heart, swelling and contracting as internal pressure waves propagate through its enormous atmosphere. When it expands, it becomes larger than Mars' orbit around our sun. Despite its relatively cool surface temperature of only 6,300 degrees Fahrenheit, Betelgeuse radiates 140,000 times more light than our sun. This incredible luminosity comes purely from its incomprehensible size. Even though each square foot of Betelgeuse's surface is dimmer than our sun's surface, the total area radiating light is so enormous that the combined output dwarfs our modest home star. Betelgeuse is losing mass rapidly. It ejects material equivalent to Earth's entire mass every 10,000 years through furious stellar winds. This supergiant is literally blowing itself apart, shedding layers of its atmosphere into space as it approaches the end of its stellar life. These winds carry processed elements, carbon, oxygen, silicon, out into interstellar space, enriching the galaxy with materials necessary for rocky planets and life. This star will explode as a supernova within the next 100,000 years. When it does, the explosion will be visible during Earth's daylight for weeks, shining as brightly as a full moon in the night sky. For a brief time, this single star will outshine entire galaxies, releasing more energy in seconds than our sun will produce in its entire 10 billion year lifetime. The distance of 550 light-years means the explosion may have already occurred, but the light hasn't reached us yet. This is one of the strangest aspects of astronomy at these scales. We're always looking into the past. The Betelgeuse we see now is the Betelgeuse of 550 years ago. If it exploded yesterday, we wouldn't know for more than 5 centuries. Inside Betelgeuse, helium is burning into carbon and oxygen in the core, with different elements arranged in layers like a cosmic onion. The star has developed a complex internal structure with shells of different nuclear burning processes. Hydrogen burning in the outer layers, helium burning deeper in, and progressively heavier elements forming toward the center. This is stellar alchemy, the cosmic forge where heavy elements are created. When Betelgeuse finally explodes, its core will collapse into either a neutron star or black hole, while the outer layers are ejected at 10% of light speed. The heavy metals forged in this explosion will spread throughout space, becoming the raw materials for future planets and eventually alien life. Every atom in your body, heavier than hydrogen, was forged in the nuclear furnace of a star like Betelgeuse or created in the explosive death of such a star. Time to catch our flight again, departing for an epic voyage of 25,450 years to the center of the Milky Way. Sagittarius A star awaits us. Now the descendants after more than 2,000 generations command our vessel. Earth has become an ancestral myth told in ancient stories, a legend of origin passed down through millennia of spacefaring generations. During the first 2,000 years of our journey toward the galactic center, the Crab Nebula appears at 6,500 light-years, the remnant of a supernova that exploded in 1054 AD. This expanding shell of glowing gas marks the violent death of a massive star, witnessed by Chinese astronomers nearly 1,000 years ago as a guest star that appeared in the daytime sky. At the heart of the Crab Nebula spins a pulsar rotating 30 times per second. A cosmic lighthouse of a neutron star containing our Sun's entire mass, compressed into a sphere just 12 miles across. This stellar remnant is so dense that a teaspoon of its material would weigh 6 billion tons. The pulsar sweeps beams of radiation across space like a lighthouse beam, pulsing with the precision of an atomic clock as it spins faster than a helicopter blade. At 8,000 years into our journey, globular clusters orbit around us like spherical swarms of ancient stars. M13 contains 300,000 stars packed into a sphere 145 light-years across. These are some of the oldest objects in our galaxy, stellar communities that formed when the Milky Way itself was young, containing stars that have been shining for over 12 billion years. At 15,000 years, stellar density increases dramatically. Stars are now separated by light months instead of light years, and the night sky would appear 200 times brighter than the view from Earth. We're entering the galactic suburbs, where stars crowd together in numbers that dwarf the sparse stellar neighborhood of our solar system. If Earth were located here, the night sky would be a tapestry of brilliant stars, with no true darkness ever falling. At 23,000 years, the spiral arms of our galaxy become visible as rivers of young blue stars and glowing pink gas clouds. These are the galaxy's star-forming regions, where massive young stars burn brilliant blue-white and ionize the surrounding hydrogen gas, creating the distinctive pink glow of stellar nurseries. We're seeing the Milky Way's active star formation in progress, the cosmic construction sites where new stellar generations are born. Stop 11, the center of the Milky Way, Sagittarius A star. 25,450 additional years, 153 quadrillion miles, 26,000 light-years from Earth, Sagittarius A star dominates the galactic center as a supermassive black hole containing 4.3 million solar masses, concentrated in a volume smaller than Mercury's orbit. This invisible monster governs the motion of everything around it through pure gravitational force. We cannot see the black hole itself, but we can observe its effects on the space and matter surrounding it. Stars near the galactic center orbit at absurd velocities. The star designated S2 reaches 4.7 million miles per hour when it passes close to the black hole, achieving 2.5% of light speed. These are the fastest moving stars known in the universe, whipped to incredible speeds by the immense gravity of our galaxy's central black hole. To maintain such velocities, they must be orbiting something extraordinarily massive, yet invisible. Material falling into the black hole forms an accretion disk that heats to millions of degrees, emitting intense X-rays detectable across the entire galaxy. This superheated matter glows with energies that would instantly vaporize any normal material. The accretion disk around Sagittarius A star occasionally flares brilliantly as clouds of gas spiral inward toward the event horizon. This region contains 10 million stars within 1 parsec cubed, a stellar density 100 million times greater than our natal solar neighborhood. If our Sun were located here, the nearest star would be only about 4 light days away instead of 4 light years. The gravitational interactions between so many closely packed stars create a dynamic, chaotic environment unlike anywhere else in the galaxy. Occasionally, Sagittarius A star devours clouds of gas, producing bright flares of radiation that last for hours or days. These feeding events illuminate the black hole's immediate surroundings, allowing astronomers to study matter in the final moments before it disappears forever beyond the event horizon. The black hole's event horizon measures 15 million miles in diameter, 17 times larger than our Sun, but completely invisible. This represents the point of no return, where the escape velocity equals the speed of light. Nothing that crosses this boundary can ever return to the universe we know. The event horizon is not a physical surface, but rather a mathematical boundary in space-time itself. Matter falling beyond the event horizon vanishes from the universe forever. Information lost to the central singularity, according to current physics. This creates one of the great paradoxes of modern cosmology. What happens to information when it falls into a black hole? Does it truly disappear, or is it somehow encoded on the event horizon? These questions probe the deepest mysteries of reality itself. Surrounding the galactic center, giant gamma-ray bubbles extend 25,000 light-years above and below the galactic disk, the mysterious Fermi bubbles, whose origin remains unknown. These enormous structures, invisible to optical telescopes but glowing brilliantly in gamma rays, suggest that our galaxy's center was far more active in the recent past, possibly experiencing violent outbursts of energy that inflated these cosmic balloons. Time to catch our flight again, lifting off toward the edge of the Milky Way, which awaits us 24,000 additional years of travel through the galactic disk. During our journey, we'll traverse entire spiral arms, plunge through molecular clouds, and pass millions of planetary systems in our trek toward the galaxy's outer boundary. Stop 12. The edge of the Milky Way. 24,000 additional years, 294 quadrillion miles, 50,000 light-years from the galactic center. At 10,000 years of travel from the galactic center looking back, the core region glows like a distant beacon surrounded by billions of densely packed stars. The central bulge of our galaxy appears as a golden glow, thick with ancient red and yellow stars that formed billions of years ago when the Milky Way was young and gas-rich. At 18,000 years, the galactic disk progressively narrows. We begin to see our galaxy in profile as a thin line of light cutting through the profound darkness. From this perspective, the Milky Way reveals its true structure. A flat disk of stars, gas, and dust, with the central bulge glowing prominently at its heart. At 22,000 years, stars become dramatically sparse as we approach the edge. Stellar density drops 1,000-fold, and darkness dominates between scattered points of light. We're entering the galactic hinterlands, where star formation ceased billions of years ago, and only the oldest, longest-lived red dwarf stars continue to shine. Here, the luminous disk ends, but the invisible halo of dark matter continues for nearly 1 million light-years, enveloping everything. The visible stars represent only a small fraction of our galaxy's total mass. Most of the Milky Way consists of mysterious dark matter that reveals itself only through its gravitational effects on the motion of stars and gas. The stars here are predominantly ancient and reddish. Star formation ceased billions of years ago in this forgotten galactic periphery. These are stellar fossils from the early universe, red dwarf stars so efficient with their nuclear fuel that they will continue burning for trillions of years, long after more massive stars have died and faded away. Looking back toward the galactic center, the Milky Way reveals itself completely, a barred spiral with 4 main arms visible in all its cosmic glory. From this external perspective, we can finally see our galaxy as it truly is. 100,000 light-years across, containing 400 billion stars, with elegant spiral arms wound around a central bar structure. Our orbital velocity is still 125 miles per second, even at this extreme distance. Dark matter dominates the gravity that keeps these outer stars bound to the galaxy. Without dark matter's additional gravitational pull, stars at this distance would escape into intergalactic space. The dark matter halo extends far beyond the visible stars, holding our galaxy together with invisible bonds. Dwarf satellite galaxies orbit here, small clusters of millions of stars gravitationally enslaved by the massive Milky Way. These galactic companions are like cosmic remora-fish, small galaxies trapped in our gravitational influence, slowly being torn apart by tidal forces as they orbit our much more massive galaxy. Stellar streams appear as thin rivers of stars being stripped from dwarf galaxies, evidence of violent and continuous galactic cannibalism. These stellar streams trace the orbital paths of smaller galaxies that have been shredded by our galaxy's gravity, their stars scattered into long trails that wrap around the Milky Way like cosmic ribbon. Time to catch our flight again, departing for a voyage of 110,000 years to the large Magellanic Cloud, a satellite galaxy awaiting us. At 50,000 years into our journey, the Milky Way shrinks to an elongated luminous patch, its 100,000 light-year disk now fitting within our field of view. At 80,000 years, the small Magellanic Cloud appears to our right at 124,000 light-years. An irregular galaxy being deformed by gravitational tides. This smaller companion galaxy is being slowly torn apart by our galaxy's gravity, its stars and gas clouds stretched into long streams by tidal forces. Stellar streams multiply throughout this region. Rivers of stars stretched between galaxies by gravitational forces, creating a map of invisible cosmic violence. These streams represent the ongoing process by which large galaxies like ours grow. By capturing and consuming smaller galactic companions over billions of years, at 100,000 years of travel, more than 5,000 human generations have passed. Earth has become a forgotten legend, and our crew members descend from millennial lineages born among the stars. The original human form has long since evolved into something unrecognizable, adapted to life in the vast emptiness between galaxies. Stop 13. The Large Magellanic Cloud. 110,000 additional years, 936 quadrillion miles, 160,000 light-years from Earth. The Large Magellanic Cloud spreads before us as an irregular satellite galaxy containing 30 billion stars. 1/3 the mass of our distant Milky Way, its shape distorted by gravitational interaction. This is no longer the pristine spiral galaxy it once was. Millions of years of gravitational harassment from the Milky Way have pulled and twisted its structure into the irregular form we see today. Within this galaxy lies the Tarantula Nebula, the largest star-forming region in our local group. So luminous that if it were located at Orion's distance from Earth, it would cast shadows on the ground. This stellar nursery measures 621 miles across, containing the star cluster R136, with hundreds of massive young stars burning with incredible brilliance. These are among the most massive stars known to exist, stellar monsters that will live fast and die spectacularly. Supernova 1987A exploded here. The first supernova, visible to the naked eye since 1604, allowing scientists to test theories of stellar collapse in real time. When this star exploded, it became a cosmic laboratory, providing astronomers with unprecedented opportunities to study the death throes of a massive star. The light from this explosion carried detailed information about the nuclear processes occurring in the star's final moments. The remnant of 1987A still expands at 6,200,000 miles per hour, its shockwave heating surrounding material to millions of degrees. This expanding bubble of superheated gas creates a glowing shell that will continue to brighten for thousands of years as the shockwave encounters more interstellar material. The explosion scattered heavy elements forged in the star's core across light-years of space. The Large Magellanic Cloud is being slowly cannibalized by the Milky Way. It will lose all its stars in 2.5 billion years, its ultimate fate being complete merger. We're witnessing galactic predation in action. The Milky Way's superior gravitational pull is gradually stripping away stars and gas from this smaller companion, feeding our home galaxy's continued growth. This galaxy contains the star R13601, the most massive star known with 315 solar masses, shining with the brightness of 8.7 million suns, yet destined to live only 3 million years. This stellar giant burns its nuclear fuel so rapidly that it will exhaust its core hydrogen in less time than it took for complex life to evolve on Earth. When it dies, the explosion will be visible across the local group. The star formation rate here is 10 times higher than in the Milky Way. This is a young, violent galaxy forging stars at a breakneck pace. The gravitational interactions with our home galaxy have compressed gas clouds in the large Magellanic Cloud, triggering intense bursts of star formation. New stellar nurseries are constantly igniting as gas clouds collide and collapse under their own gravity. Time to catch our flight again, departing for a gigantic leap of 2.34 million years to Andromeda, the largest galaxy in our local group. During this epic journey spanning millions of years, the descendants of 117,000 human generations now maintain our vessel with the chronology of our journey recorded in digital monuments that preserve the memory of our cosmic odyssey. At 1 million years into our journey, the Milky Way and large Magellanic Cloud shrink to small spirals in the distance. Our entire history contained within those luminous whirlpools. Everything we've experienced so far, every star we've visited, every nebula we've passed through, now fits within 2 small patches of light receding behind us. At 1.8 million years, the Triangulum Galaxy, M33, glows to our left at 2.8 million light-years. A spiral containing 40 billion stars, this galaxy possesses well-defined spiral arms, visible even from this enormous distance, making it the 3rd largest galaxy in our local group, after Andromeda and the Milky Way. At 2.2 million years, dozens of dwarf galaxies dot the space around us. M32 and M110 orbit Andromeda like faithful, subordinate satellites. These smaller galaxies represent the most common type in the universe. Dwarf galaxies containing millions to billions of stars, gravitationally bound to larger galactic neighbors. Stop 14. The Andromeda Galaxy, M31. 2.34 million additional years, 147 quintillion miles, 2.5 million light-years from Earth. Andromeda spreads before us as the largest galaxy in our local group, containing 1 trillion stars, 2.5 times more populous than our distant Milky Way. This is a mature spiral galaxy in the prime of its existence, a stellar metropolis that dwarfs our home galaxy in both size and stellar population. With a diameter of 137,000 light-years, more than twice the width of the Milky Way, Andromeda gravitationally dominates the entire local group of galaxies. This galactic giant exerts its influence across millions of light-years, slowly pulling smaller galaxies into its gravitational embrace and orchestrating the movements of our entire cosmic neighborhood. The galaxy's mysterious double nucleus contains P1 and P2, separated by 4.2 light-years, with a central black hole in P2 containing 230 million solar masses. This supermassive black hole is 50 times larger than Sagittarius A star in our home galaxy, representing gravitational power incomparably superior to our natal galactic center. Andromeda approaches us at 68 miles per second. It will collide with the Milky Way in 4 billion years, creating a giant elliptical galaxy that astronomers have already nicknamed Milkomeda. This future collision will fundamentally reshape both galaxies, scattering stars into new orbits and triggering massive bursts of star formation as gas clouds collide and compress. Evidence shows that Andromeda has already devoured at least 2 dwarf galaxies in the past. Astronomers have found stellar remains in its halo, proof of ancient cannibalism. These galactic meals have contributed to Andromeda's impressive size. Like most large galaxies, it has grown through a process of cosmic predation, absorbing smaller galactic neighbors over billions of years. The star formation rate here is lower than in the Milky Way. Andromeda is a mature galaxy that has passed its stellar reproductive peak. Most of its gas has already been converted into stars or heated to temperatures too high for new star formation. This galaxy represents what the Milky Way might look like in several billion years. Massive, mature, but past its prime star-forming era. M32 orbits so close that it causes perturbation in Andromeda's spiral structure. Hydrogen arms displace 2,500 light-years from the stellar arms. This gravitational interaction demonstrates how even small satellite galaxies can influence the structure of their massive hosts, creating asymmetries and distortions in spiral patterns. M110 is being stretched by gravitational tides, elongated by Andromeda's force, which progressively strips away stars over millions of years. This process of tidal stripping will eventually reduce M110 to a sparse stream of stars scattered along its orbital path around Andromeda. Time to catch our flight again, lifting off toward the frontier of our local group, which awaits us 7.5 million additional years of travel. At 4 million years into this journey, Andromeda and the Milky Way form a dominant pair visible in the distance, 2 luminous whirlpools commanding a group of 80 galaxies. At 6 million years, dwarf galaxies spread in all directions. NGC 185, NGC 147, IC 10, each containing tens to hundreds of millions of stars. These smaller galactic communities represent the building blocks of cosmic structure, the fundamental units from which larger galaxies like Andromeda and the Milky Way have grown through mergers and accretion. At 7 million years, darkness progressively dominates. The space between galaxies approaches near absolute vacuum with only 1 atom per cubic yard. This is the realm of intergalactic space, where matter becomes so sparse that entire cubic miles might contain only a handful of atoms. We're entering the cosmic voids that separate galactic neighborhoods. By this point in our journey, more than 375,000 human generations have passed since our original departure from Earth eons ago. The beings aboard our vessel have evolved far beyond recognition. Their consciousness adapted to the vast scales of cosmic time and distance that now define their existence. Stop 15. The frontier of the local group. 7.5 million additional years. 588 quintillion miles, 10 million light-years from Earth. The local group contains at least 80 known galaxies within 10 million light-years of total diameter. This represents our immediate cosmic neighborhood, a gravitationally bound collection of galaxies that includes everything from massive spirals like Andromeda and the Milky Way, down to tiny dwarf galaxies containing only a few million stars. The total mass reaches 2 trillion solar masses, but 95% consists of invisible dark matter that keeps everything gravitationally bound. What we can see, the brilliant spirals, the glowing star clusters, the shining nebulae, represents only a tiny fraction of the local group's actual mass. The vast majority of matter here remains completely invisible, revealing itself only through its gravitational effects. All galaxies orbit around a barycenter located between the Milky Way and Andromeda, the center of mass for the entire galactic group. This invisible point in space governs the motion of 80 galaxies, determining their orbital paths through a gravitational choreography that has been unfolding for billions of years. The escape velocity is 37 miles per second. Any galaxy moving slower than this remains gravitationally trapped within the group forever. This defines our cosmic prison, the boundary beyond which galaxies can break free from the local group's collective gravitational embrace and drift away into the larger universe. Here ends our immediate cosmic neighborhood. Beyond this point, other structures and superclusters dominate the space around us. The local group is a small structure compared to what awaits ahead, merely a cosmic suburb on the periphery of the Virgo supercluster. Time to catch our flight again, departing for a 50-million-year journey to the Virgo cluster, a galactic metropolis awaiting us. At 20 million years into this voyage, the local group shrinks to a luminous point. Everything we've known reduced to a cosmic grain of sand in the vast darkness. At 35 million years, galaxies begin to thicken progressively around us, transforming from isolated points to a growing, concentrated swarm. We're approaching one of the universe's great galactic cities, where thousands of galaxies crowd together in gravitational communion. At 48 million years, M87 emerges as a bright beacon in the distance, with a relativistic jet 3,100 miles long shooting from its galactic nucleus. This jet ejects matter at 99% of light speed, powered by a central black hole containing 6.5 billion solar masses. M87 holds special significance in human history. It was the first galaxy to have its black hole photographed by humanity in 2019 through the Event Horizon telescope. That historic image revealed the shadow of the black hole's event horizon silhouetted against the glowing accretion disk, the first direct visual evidence of these cosmic monsters that had been predicted by theory for decades. At 50 million years of travel, 2.5 million human generations have descended from our original crew members, an unbroken lineage through deep time. Earth has become less than a myth. It's now an abstract concept studied by cultural archaeologists aboard our vessel as they attempt to reconstruct our lost origin. Stop 16. The Virgo cluster. 50 million additional years. 352 quintillion miles, 60 million light-years from Earth. The Virgo cluster spreads before us, containing at least 2,000 galaxies within 9.3 million light-years diameter, a densely populated cosmic metropolis. This represents one of the universe's great galactic cities, where spiral and elliptical galaxies crowd together in numbers that dwarf our modest local group. The total mass reaches 1.2 quadrillion solar masses. The collective gravitation dominates the entire surrounding region of space across hundreds of millions of light years. This gravitational influence extends far beyond the cluster's visible boundaries, pulling in smaller galaxy groups from vast distances and orchestrating the large-scale structure of our cosmic region. M87 reigns at the center with its 6.5 billion solar mass black hole. 1,500 times more massive than Sagittarius A star in our natal galaxy. This supermassive black hole represents gravitational power on scales that dwarf anything in our home region. Its event horizon spans 16 billion miles, larger than Neptune's entire orbit around our distant sun. Our local group is being pulled toward Virgo at 186 miles per second. We're falling inexorably toward this gigantic gravitational well. This motion has been ongoing for billions of years, drawing our entire galactic neighborhood deeper into the Virgo cluster's sphere of influence. Eventually, in the far future, the local group will merge with this vast galactic metropolis. The temperature of intergalactic gas reaches 54 million degrees Fahrenheit. So hot, it emits X-rays detectable across the entire cluster. This superheated plasma fills the space between galaxies, heated by the gravitational compression of infalling matter and the shock waves created by galactic collisions. At these temperatures, atoms move so fast that electrons are stripped away, creating a tenuous but incredibly hot medium. Galaxies collide frequently here due to extreme density. Galactic mergers are common, creating massive elliptical galaxies. The close proximity of so many galaxies leads to gravitational interactions that distort spiral arms, trigger bursts of star formation, and ultimately cause galaxies to merge into larger structures. This cosmic violence shapes the evolution of galactic communities. NGC 4038 and NGC 4039 form the antennae galaxies, a collision in progress with tidal tails extending hundreds of thousands of light years. These galactic appendages, drawn out by gravitational forces during the collision, stretch across distances larger than the entire Milky Way. The collision has triggered massive bursts of star formation as gas clouds are compressed and heated. Time to catch our flight again, departing for a 140 million-year journey to the Great Attractor, a mysterious gravitational anomaly awaiting us. At 80 million years into this voyage, superclusters multiply around us, each structure containing dozens of galactic clusters like the one we're leaving behind. At 120 million years, the perturbed Hubble flow becomes visible. Galaxies stream in a common direction like cosmic rivers converging inevitably. We're witnessing the large-scale structure of the universe itself, where galaxies don't simply move away from each other due to cosmic expansion, but are also pulled toward massive gravitational concentrations that distort the smooth expansion of space. At 130 million years, the Norma cluster appears at 206 million light-years, massive but hidden behind our natal galactic disk. This cluster contains hundreds of galaxies, but remained unknown for decades due to the zone of avoidance, where our own galaxy's dust and gas block our view of the distant universe. Only through infrared and radio observations can astronomers peer through this cosmic fog. At 140 million years, 7 million generations have passed. Our crew members have become a species genetically distinct from original terrestrial humans. Genetic memory preserves fragments of Earth's DNA, but the phenotype has changed drastically through millennia of adaptation to life aboard our vessel. These beings represent humanity's ultimate evolutionary destiny, consciousness adapted to cosmic scales, minds shaped by the vast emptiness between galactic superclusters. Stop 17, the Great Attractor. 140 million additional years, 1.2 sextillion miles, 200 million light-years from Earth. The Great Attractor reveals itself as a gravitational anomaly with mass equivalent to 100,000 galaxies, concentrated in a relatively small region of spacetime. This invisible monster pulls thousands of galaxies, including our distant Milky Way, at velocities of 373 miles per second toward its unseen center of mass. Located behind the zone of avoidance, where our home galaxy's disk blocks direct observation, the Great Attractor was discovered through the peculiar motions of galaxies. Astronomers noticed that galaxies weren't moving randomly through space, but were all flowing in the same direction, as if being pulled by some enormous gravitational source hidden from view. But this isn't the final destination of our cosmic fall. There exists an even larger structure called Laniakea that contains the Great Attractor and 100,000 other galaxies. Laniakea means immeasurable heaven in Hawaiian, a supercluster spanning 323 million light-years in diameter, containing our entire cosmic neighborhood. The center of mass of Laniakea lies at 323 million light-years away. We're all falling slowly toward it through space-time. This motion has been ongoing since the early universe, as gravity slowly draws matter together into ever larger structures. Our entire local group, the Virgo cluster, and thousands of other galactic communities are all participants in this slow cosmic migration. The great attractor sits in the direction of the southern triangle, and Norma constellations as seen from distant Earth. The Norma cluster, Centaurus cluster, and other massive galactic collections contribute to the total mass of this gigantic gravitational anomaly. Together, they create a gravitational influence that reaches across hundreds of millions of light years. Time to catch our flight again, departing for an 800 million year journey to the Sloan Great Wall, the largest structure known for decades. At 300 million years into our voyage, cosmic filaments become evident. Webs of galaxies connecting superclusters like cosmic neurons in a universe-spanning neural network. At 500 million years, gigantic cosmic voids appear, regions spanning 93 million light-years almost completely empty, containing fewer than 10 galaxies. These voids represent the flip side of cosmic structure, vast bubbles of near emptiness separated by thin walls of matter. The universe resembles a cosmic foam, with galaxies concentrated along the bubble walls, while the interiors remain nearly vacant. At 700 million years, filamentary structure completely dominates. Galaxies aren't distributed randomly, but follow a three-dimensional web pattern. This cosmic web represents the largest structure in the universe, a scaffolding of dark matter and galaxies that emerged from tiny quantum fluctuations in the early universe and grew over billions of years through gravitational collapse. At 800 million years, 40 million generations have passed. Our crew members are no longer recognizable as original human descendants. Individual consciousness has been replaced by a collective mind, a digitally connected hive mind that maintains memory of our journey across stellar geological eras. Stop. 18. The Sloan Great Wall. 800 million additional years, 5.9 sextillion miles, 1 billion light-years from Earth. The Sloan Great Wall stretches before us as the largest structure known for decades. 850 million light-years in length, a wall of galaxies separating two immense cosmic voids. This structure challenges our understanding of how matter can organize itself on such enormous scales, representing a limit to the size of coherent structures in the observable universe. This cosmic wall contains 30 superclusters and tens of thousands of galaxies organized in an elongated, narrow but extremely extensive filament. The galaxies aren't randomly scattered, but follow a coherent pattern, like pearls strung along an invisible cosmic thread that spans distances almost incomprehensible, even at our current scale of understanding. The wall's thickness measures only 9.3 million light-years, an extremely elongated structure like a cosmic sheet of paper traversing the universe. Despite its immense length, the Sloan Great Wall is remarkably thin, creating a two-dimensional structure in three-dimensional space that separates vast, empty regions. This formation emerged from primordial quantum fluctuations amplified by gravity over 13.8 billion years of cosmic evolution. In the early universe, tiny variations in density, differences of less than 1 part in 100,000, were slowly amplified by gravitational attraction until they became these enormous structures we observe today. The density of galaxies here is 5 times higher than the cosmic average, a concentration resulting from gravitational collapse of primordial overdensities. This represents one of the universe's great construction projects, where billions of years of gravitational attraction have gathered matter into this enormous wall, while leaving vast voids on either side nearly empty. The Sloan Great Wall was discovered by the Sloan Digital Sky Survey in 2003 through three-dimensional mapping of galaxy positions and distances. This discovery required surveying millions of galaxies to reveal the wall's full extent, demonstrating how recent our understanding of the universe's largest structures really is. Since then, even larger structures have been discovered. The huge Large Quasar Group, spanning 2.5 billion light-years, and the Hercules Corona Borealis Great Wall, stretching 6.2 billion light-years. These discoveries challenge the cosmological principle of homogeneity, which suggests the universe should appear uniform on scales larger than 186 million light-years. These gigantic structures push the boundaries of what current cosmological models predict should be possible. They represent the largest coherent structures that gravity has had time to assemble since the Big Bang, marking a transition between the structured universe we know and the smooth, homogeneous cosmos that theory predicts on the largest scales. Time to catch our flight again, departing for a 9-billion-year journey to a distant quasar. We'll look deeply into the cosmic past. At 3 billion years into this voyage, galaxies become smaller and more blue, as we're looking into the past and seeing younger galactic communities. At 5 billion years, the star formation rate increases dramatically. The universe was more active billions of years ago, with more stars being born. We're witnessing the cosmic dark ages ending, when the first galaxies were forming and the universe was emerging from its primordial simplicity into the complex, structured cosmos we know today. At 7 billion years, galaxies appear less organized. Spirals are rare, with many irregular galaxies interacting violently in frequent collisions. This was the epoch of galactic violence, when the universe was smaller, denser, and galaxies collided far more frequently than in the modern cosmos. At 9 billion years, 450 million generations have passed. Our crew members have become post-biological entities, integrated into our vessel as distributed consciousness. The memory of Earth exists only in quantum archives, its meaning lost, except as an archaeological curiosity of forgotten origin. These beings represent the ultimate evolution of intelligence, minds expanded across cosmic scales, consciousness adapted to the vast emptiness and immense timescales of the universe itself. Stop. 19. Distant quasar. 9 billion additional years, 588 sextillion miles, 10 billion light-years from Earth. We're seeing this galaxy as it existed 10 billion years ago, when the universe had only 3.8 billion years of age. This is deep-time archaeology, observing the cosmos when it was barely a quarter of its current age. The galaxy before us represents the universe in its violent youth, when conditions were drastically different from the serene cosmic environment we've grown accustomed to. Back then, galaxies were smaller, more chaotic, and engaged in frequent violent interactions that shaped their evolution. The quasar blazes with luminosity equivalent to 100 trillion stars, all emitted from a region smaller than our original solar system. This incredible brightness comes from matter spiraling into a supermassive black hole at the galaxy's core, heating to millions of degrees as it accelerates toward the event horizon. The energy released in this process outshines entire galaxies, creating a cosmic lighthouse visible across billions of light-years. To put this luminosity in perspective, if you could somehow capture all the energy this quasar emits in a single second, it would power human civilization for trillions of years. The physics involved operate at extremes that challenge our understanding. Matter falling into the black hole converts roughly 10% of its mass into pure energy, the most efficient power generation process known in the universe, far exceeding nuclear fusion. The central black hole contains 10 billion solar masses, consuming 1 solar mass per year through its superheated accretion disk. This feeding rate represents cosmic gluttony on an unimaginable scale. Every year, this monster devours material equivalent to our entire sun, converting a fraction of that mass into pure energy through gravitational compression and friction in the accretion disk. The accretion disk itself spans several light-years, larger than the distance from our sun to the nearest stars. Within this disk, matter reaches temperatures of millions of degrees, hot enough to emit X-rays and gamma rays. The disk's inner edge orbits the black hole at significant fractions of light speed, creating relativistic effects that twist spacetime itself. Relativistic jets shoot perpendicular to the accretion disk, accelerating matter to 99.9% of light speed across millions of light years. These cosmic particle accelerators create beams so energetic they remain coherent across galactic distances, punching through the intergalactic medium like cosmic blowtorches powered by gravitational energy. The jets carry away excess angular momentum, allowing more matter to spiral into the black hole. These jets are among the most energetic phenomena in the universe, containing particles with energies that dwarf anything achievable in earthly accelerators. When these jets interact with surrounding gas clouds, they create enormous radio lobes that can extend millions of light years beyond the host galaxy. The energy contained in these structures represents the accumulated feeding activity of the central black hole over millions of years. Quasares were common in the young universe, but are nearly extinct today. The golden age of supermassive black hole feeding has passed. In the early cosmos, galaxy collisions were frequent due to the smaller size of the universe and higher density of matter. These collisions provided abundant fuel for central black holes, triggering the brilliant quasar phase we observe. As the universe expanded and cooled, galaxies spread apart, and gas became more diffuse. Modern supermassive black holes, like the one in our distant Milky Way, are essentially starving. They occasionally flicker to life when a star wanders too close or a gas cloud falls inward, but nothing approaches the sustained feeding frenzy that powered quasars in the cosmic dawn. The quasar's radiation is so intense it ionizes gas in neighboring galaxies millions of light years away, creating stellar dead zones. This represents environmental destruction on cosmic scales. The quasar's energy output sterilizes vast regions of space, heating gas to temperatures too high for star formation and preventing the birth of new stellar generations across volumes that could contain thousands of galaxies. This process, called quasar feedback, may have been crucial in regulating galaxy formation in the early universe. Without this mechanism to shut down star formation, early galaxies might have converted all their gas into stars too quickly, creating a universe very different from the one we observe today. The host galaxy is undergoing violent merger with another galaxy. The collision feeds the central black hole with abundant gas. We're witnessing cosmic violence that triggers the quasar's fury. When galaxies collide, gravitational forces disrupt their orderly rotation, sending gas clouds plunging toward the center, where they provide fuel for the supermassive black hole. These galactic mergers were the driving force behind early cosmic evolution. Small proto-galaxies merged to form larger structures, with each collision potentially triggering a quasar phase. The hierarchical assembly of cosmic structure proceeds through this process of merging, with smaller structures combining to form progressively larger ones. The star formation rate reaches 2,200 pounds of stellar material per year, 1,000 times greater than the mature Milky Way of our era. This galaxy is experiencing a cosmic baby boom, forging stars at a rate that would exhaust its gas supply in just a few 100 million years. The collision has compressed gas clouds throughout both galaxies, triggering intense bursts of star formation. These newly formed stars are predominantly massive and short-lived, burning through their nuclear fuel in just a few million years before exploding as supernovae. The rapid succession of stellar births and deaths enriches the galaxy with heavy elements, while also heating and dispersing gas through supernova explosions, eventually shutting down the star formation burst. Time to catch our flight for the last time, departing for our final voyage of 3.8 billion years to the edge of the observable universe. At 1 billion additional years, the first galaxies emerge small, irregular, and blue from short-lived massive stars. These are the universe's first attempts at galaxy formation, crude, violent, and inefficient compared to the elegant spirals we've known. These primordial galaxies lack the heavy elements necessary for complex chemistry. Composed almost entirely of hydrogen and helium from the Big Bang, they can only form massive stars that burn hot and die young. There are no Earth-like planets here, no carbon or oxygen or silicon, just the simplest atoms created in the cosmic dawn. At 2 billion years, matter organizes into primordial structures, protoclusters of galaxies beginning to form gravitationally. We're witnessing the birth of cosmic architecture as gravity slowly gathers the universe's sparse matter into the first large-scale structures. These protostructures will eventually become the galaxy clusters and superclusters we've visited, but now they're just loose associations of young galaxies. The cosmic web is beginning to emerge from the smooth distribution of dark matter left over from the Big Bang. Tiny variations in density, amplified by billions of years of gravitational growth, are creating the first filaments and nodes that will define large-scale structure. This is the universe learning how to organize itself into the patterns we observe today. At 3 billion years, light becomes reddened by extreme redshift. We're seeing close to the Big Bang when space expanded rapidly. The wavelengths of light are stretched by the expansion of space itself, shifting visible light into infrared as we observe increasingly distant and ancient cosmic epochs. We're approaching the limits of electromagnetic observation. At 3.7 billion years, primitive galaxies collide frantically. Each collision triggers an explosion of star formation, fueling exponential growth. This was the era of cosmic construction, when the universe's basic structures were being assembled through violent processes that dwarf anything in the modern cosmos. Galaxy formation was a chaotic, inefficient process driven by gravitational collapse and merger. At 3.8 billion years, 190 million generations have elapsed since our departure. Our crew members have become quantum consciousness distributed throughout our vessel organism. These beings represent the final transformation of intelligence, minds that have transcended individual existence to become part of a cosmic awareness spanning the observable universe. They are no longer recognizable as descendants of terrestrial humanity. Stop 20. The edge of the observable universe. 3.8 billion additional years. 812 sextillion miles. 13.8 billion light-years from Earth. We've arrived at the observation limit. This isn't a physical edge, but a horizon beyond which light hasn't yet had time to reach us. This boundary represents the ultimate limit of knowledge, the point where information about the universe simply ceases to exist from our perspective. Beyond this horizon, events may be occurring, but their light will never catch up to us due to the expansion of space. This cosmic horizon is fundamentally different from any boundary we've encountered. It's not a place in space, but a limit in time, defined by the finite age of the universe and the finite speed of light. No matter how long we wait, this boundary will always exist, though it will gradually expand as more distant light has time to reach us. The observable universe has a radius of 28.9 billion light-years due to space expansion while light traveled to us. This might seem paradoxical. How can we see objects farther than 13.8 billion light-years in a universe that's only 13.8 billion years old? The answer lies in cosmic expansion. While light was traveling toward us, space itself was stretching, carrying those distant objects even farther away. This expansion means that objects we observe at the cosmic horizon are now much farther away than they were when their light began the journey to us. The galaxy whose ancient light we observe here is now approximately 90 billion light-years away, carried by the expansion of space to distances that would take light 3 times the current age of the universe to traverse. The observable universe contains approximately 2 trillion galaxies, each with hundreds of billions of stars. The total number of stars exceeds 10 sextillion. This represents only what we can see. The actual universe may be infinite, containing countless trillions more galaxies beyond our observational horizon, forever hidden from our view by the fundamental limitation of light speed and cosmic expansion. Consider the magnitude of these numbers. 10 sextillion stars means 10 followed by 21 zeros. This exceeds the number of grains of sand on all Earth's beaches, the number of cells in all living organisms, the number of seconds that have passed since the Big Bang. Yet this represents only the visible portion of what may be an infinite cosmos. What we observe here is the universe at 380,000 years of age. Hot plasma cooling, atoms forming for the first time in cosmic history. This is the cosmic microwave background radiation, the afterglow of the Big Bang. Before this epoch, the universe was opaque to light. A hot, dense fog of free electrons and protons that scattered photons endlessly, preventing them from traveling freely through space. During this period, called the Epoch of Recombination, the universe cooled enough for electrons to combine with protons, forming neutral hydrogen atoms. For the first time since the Big Bang, space became transparent to light. The photons that had been trapped in the hot plasma were suddenly free to travel across the cosmos, carrying with them an image of the universe as it existed in its infancy. The cosmic microwave background appears as uniform glow, the echo of the Big Bang when the universe first became transparent to light. This radiation has been traveling through space for 13.8 billion years, cooling and redshifting until it now appears as microwave radiation at -454 degrees Fahrenheit. This ancient light carries the baby picture of the universe, showing conditions when it was only 380,000 years old. By studying tiny variations in this background radiation, cosmologists can determine the universe's composition, geometry, and ultimate fate. It represents the oldest light we can ever observe. Current temperature fluctuations in this radiation of only 18 thousandths of a degree reveal the seeds of galaxies and structures that would come to exist. These tiny variations in temperature represent quantum fluctuations from the early universe, amplified by cosmic expansion and gravity into the vast structures we've journeyed through. Beyond this horizon exists more universe, but we can never see it. Space expansion carries light away faster than it can travel. This represents a fundamental limit to knowledge. No matter how long we wait or how powerful our telescopes become, we can never observe what lies beyond this cosmic horizon. Space itself is expanding so rapidly at these distances that light cannot overcome the recession velocity. If we could see beyond, we would find more galaxies, more structures, possibly extending forever in an infinite or closed universe. The universe beyond our horizon might be similar to what we've observed, or it might be radically different. Without observational access, we can only speculate about the true extent and nature of cosmic reality. Our journey of 13.8 billion light-years at light speed has covered the entire observable history of the cosmos since the Big Bang. We've traveled from a familiar human world to the theoretical limit of existence, traversing 20 incomprehensible scales of magnitude progressively. From the moon at 1.28 seconds to the cosmic edge at 13.8 billion years, each stop revealed a universe larger than the previous. We began with worlds we could walk across and ended at structures so vast they challenged the very concept of size. Each scale has humbled us with its immensity. In the profound silence of this final edge, we look back seeing all creation spread behind us. 13.8 billion years of cosmic history. Here at the boundary between the known and unknowable, we confront the ultimate mystery of existence itself. And we realize the true scale of the universe doesn't merely transcend human comprehension, it transcends every category of thought conceivable by any mind. If you're still awake, it's because the content was really good. So, take a moment, leave a like and subscribe to the channel, it helps a lot. And if you want to keep watching, just click on the video that's appearing right now. I'll see you there.